Hi, hello everyone. Good evening to all of you. Welcome to ace online platform. So myself, G. Venkateswarlu, faculty at Ace Engineering Academy, as part of Computer Science and Information Technology department. So in our previous session, we have discussed about how to prepare operating system with respect to GATE examination. This is what we have covered in our previous session. And we also pointed out there are some topics on which we have repeatedly we have some questions which is given by IIT Kanpur. That is also we have pointed out and we emphasized it, right? So now in this session, what we are going to see, some important concepts of operating system we are going to recall. Like that recall is also with respect to some previous year GATE questions. Okay, so I just want to tell you that this session is going to be, you can consider this question, this particular session as concept through questions. You can consider like this, concept through questions. Okay, and those questions whichever we are going to discuss now, those questions are given by IIT Kanpur in previous year like 2015, 2007 like that. So those questions we are going to target in this session. Okay. Right. So let's look into the first question. So this is the question we have from memory management, and the concept is paging, right? So yesterday, in our previous session, we clearly seen that on paging, every year we have one question which is given by IIT Kanpur. So that's why I just want to tell you this. I just want to give you some information related to this paging concept. So how to solve this particular question, so what is the main importance of the paging? Try to recall. The main importance of the paging is, so if you consider paging here, what is the main concept of paging is and what is the main need of paging is, you know that this is my CPU and this is our main memory. So this main memory, let's say this is my main memory. So this main memory is always associated with physical address. But this CPU always generates the logical address, right? So it is generating the logical address, but this memory is always associated with the physical address. Then by considering this logical address, if this CPU directly goes to the main memory, is it able to get its desired data? In the sense, no, because there is a mismatch between this logical address and physical address. So since we have a mismatch between the logical address and physical address, this CPU is unable to get its desired data by going through this logical address, right? So it means that as the memory is associated with the physical address, if the CPU wants to get its desired data, compulsory the generated address, which is the logical address, is there, that needs to be converted to physical address. So for that purpose, we required this paging concept. So this is the first point which you have to understand. Then, what is the procedure? How we are converting this logical address into physical address? So how we can convert this logical address into physical address, in the sense, we all know that if logical address is there, according to the paging concept, logical address is divided into two parts. What are the two parts? One is page number, another one is offset. In the same way, on the other hand, we have the physical address. So this physical address also divided into two parts. One is frame number, another one is offset. So this is what first point which you have to consider. Then coming to the second point. So what is the second point? Let's say if you consider 2 power n is the page size, 2 power n is the page size, and 2 power m is the logical address space. If 2 power n is the page size and 2 power m is the logical address space, then the most significant portion of logical address is m minus n bits, and the least significant portion of logical address is n bits. So this is what we have to consider as a second, we have to consider this point as a third point, right? So our second point here. So if 2 power n is the page size and 2 power m is the logical address space, then the most significant portion, as part of the logical address, most significant portion is P. That P length is m minus n bits. But the least significant portion of this logical address is D, which you can call offset. So this is the length of n bits. In the same way, here also, if 2 power n is the frame size, if 2 power n is the frame size and 2 power m is the physical address space, then the most significant portion of this physical address, which is the frame number, is m minus n bits, and the least significant portion D is n bits. This is right? So n bits and m minus n bits. So in this context, in this particular given question, if you verify, of course the memory is byte addressable, fine. 32-bit logical address is given. So logical address is given as 32 bits. And the page size is given 4 kilobyte. So page size is given as 4 kilobyte. So if I convert this into powers of 2, then this is going to be 2 power 12 bytes. And this logical address, if this logical address is 32-bit, then the logical address space is going to be 2 to the power of 32 bytes. So logical address is in terms of bits, but logical address space is going to be in terms of bytes. Mind this sensible point. It is in terms of bits, but this is in terms of bytes. On the other hand, it is also given that page table entry. So page table entry I can write as E. So that E is given as 4 bytes. 4 bytes. Okay, right. So now, if 2 power m is the physical address space, logical address space, 2 power m, so this is my m value, and 2 power n is my n value. Then this logical address, as we mentioned, the logical address is divided into two parts. So what are the two parts? The first part is page number, another one is D, offset. So m is how much? 32, and n is how much? 12. So m minus n bits. M minus n bits in the sense your page number is 20 bits. And D means what? N bits. That's what you have listened, that's what we have written. No? D value is n bits. So what is the n value here? 12. So that simply 12. Right? So this is the way how you can convert, how you can divide your logical address into two parts. Right? So then it is asking you to calculate size of the page table. So page table size we want to calculate. So what is this page table size? So the diagram for this paging concept, if you verify, the diagram for the paging concept, if you verify, so diagram for the paging concept, how we have, try to recall. So if you consider this is our CPU, and the CPU is generating the logical address, which is being divided into two parts. One is page number, another one is offset. And this is our physical memory, which is associated with the physical address. This is my physical memory. PAS or else physical memory you can write, right? So this physical address is divided into two parts. One is, that frame, number and offset. Okay. So to convert this logical address into physical address, we are using a table here which is called page table. So this is my page table. This is my page table. So this page table, what is the format of this page table entry is frame number and keeping information. This is the page table entry format. So page table entry format is given already in the question. So what is the page table entry size? 4 bytes. It means indirectly it has given that frame number plus bookkeeping information is given, but according to the paging concept, bookkeeping information is optional. This is optional. But frame number is mandatory. Frame number is mandatory, but bookkeeping information is optional. Right? So now verify here. And since we have a page table, in the page table we are having entries, right? So, and that too, this page table can have an index. So who is going to act as an index? In the sense, page number is acting as an index to the page table. And that these are the entries we are having. So if my page number size is, let's say, if the number of bits that I am using to represent the page number is 8, if you consider 3-bit, if I am using 3-bit page number, if I am using 3-bit page number, if I am using 3-bit page number, then I am going to have 8 number of pages. What are the 8 number of pages? 000, 001, 010, 011, 100. So like this we are going to have 8 pages. So as the page number is acting as an index to this page table is also going to have how many number of entries? Equals to the number of pages. So the number of pages in LAS is equals to the number of entries in the page table, because page number is acting as an index here. And this offset and this offset both are same. So from this page number or from this page table, we can get the frame number. In which frame number of this requested page of the CP is available, that we can come to know from the page table. So after getting the frame number, we are copying here and we are going to physical memory. This is what the diagram which we can consider for logical address to physical address conversion in the case of paging concept. So the same scenario we are applying now. Look at to answer to this question. So now I required page table size. I just mentioned page table size is equals to, it can have some entries as well as every entry can have some size which is n into e. So what is that n? N is equals to number of entries in the page table. Number of entries in the page table. And you know that number of entries in the page table is equals to the number of pages in LAS. The number of pages in LAS. The number of pages in LAS. So how many number of entries in the page table we are having? That equals to number of pages in LAS, which means that the number of pages in LAS, what is the formula we have? LAS by page size. So what is the LAS here according to this? 2 to the power of 32 bytes by, what is the page size? 2 power 12 bytes. So which is going to be 2 to the power of 20. So 2 to the power of 20 number of entries we are having in the page table into every entry size is 4 bytes. So then this is going to be 4 MB. 4 MB. So as the question is asking you in terms of megabytes, the page table size in terms of megabytes, the answer for this question is 4. So this is one technique, one way of solving this question. And without using this formula, also I can easily answer to this question. How can I answer? Have a look. Without using this formula, see, according to this, if you verify, your number of bits to represent the page number is 20. If you are using 20 bits to represent one page, then such pages, how many you can have? 2 to the power of 20, correct? So it means that the number of entries in the page, the number of pages in your LAS is equal to number of entries in your page table. So as you are using 20 bits to represent one page, so I can write like this. So to represent a page, we are using 20 bits. 20 bits. So according to this particular question, to represent a page we are using 20 bits. Then total pages we can have, total pages we can get as how much it is? 2 to the power of 20. So 2 to the power of 20 pages we can get. And you know that the number of pages in LA equals to number of entries in the page table. So 2 to the power of 20, which is also I can consider as number of entries in page table. So number of entries in page table I know, and number of entry size is also given. So 2 to the power of 20 into 4 bytes, which I can get as 4 MB. So look at, without using this formula, I can also answer this question like this. Okay. So anyway, you can use either this technique or this technique, any technique. Using formula, one way of solving this question. Without using the formula, this is another way of solving this question. But anyway, it is going to be same answer. So 4 is the answer for this question. Okay. So I believe you are clear with this. So let's move to next question. Yeah. So this is the question we have from, inter-process synchronization, right? So let's look into this question. The following two functions, P1 and P2, that share a variable B. So both processes on P1 are sharing a variable B with an initial value of 2. So it means the B value is 2 here. Okay, so P1 and P2. So the code is being given. So what is the code of P1? C is equals to B minus 1 and B is equals to 2 into C. What is the code for P2? D is equals to 2 into B and B is equals to D minus 1. So the number of distinct values that B can possibly take after the execution is. So this is what the question we have. Let's look into this question solution. Right. So coming to this question. So first I am considering case 1. I can say without preemption, I am not taking any preemptions, okay? Without preemption, okay? Without preemption, I am considering case 1 here. So what is the case 1 I am considering? So without preemption, I am considering case 1. So what is the case 1? I just executing P1 first and then I am executing P2. Without preemption, first I am executing P1 and then I am executing P2. So what is the B value? 2. So P1 C is equals to B minus 1. What is the B value? 2. So that the C value is 1 here, right? Then B is equals to 2 into C. So what is the C value? 1. So that B is equals to 2 into 1, which is going to be B value is 2 now. So P1 is storing value 2 into the B, okay? So after that, now P2 is executing. So what is the B value now? 2. Then D value is 4. Then B value is going to be 3. So at the end, after execution of P1 and P2, let's say after execution of P1, if I execute P2, then the final value that is going to be saved in the B is 3. So in this case 1, I am getting B value is 3. This is what the first possible value into the B without preemption case. Okay, right. So then coming to the second case, what is the second case we are going to consider? In the same non-preemption, without any preemptions, first I am executing P2 and then I am executing P1. Then what is the value that I am going to have? Verify. So first I am executing P2. So first I am going to execute P2. So P2, what is the B value? 2. So D is equals to 2 into B. 2 into B in the sense what? D is equals to 4. Then B is equals to D minus 1. It means B value is 3. So after finishing of P2, you have B value is 3. Now, we are executing P1. So C is equals to B minus 1. What is the B value? 3. Then C value is 2. Then B is equals to 2 into C. What is the C value? 2. So B is equals to 2 into 2, which is going to be 4. So after execution of P2, then if I execute P1, then what is the value that I am saving into the B is 4. So 2 different values I got so far. Okay. So this is what without preemption. But if you consider with preemption, if we consider with preemption, so case 1 with preemption, case 1 we are considering. So what is the case 1 we are considering here? Have a look. So what is the case 1 we have? So first I am starting the execution of P1 and then I am taking the preemption towards the P2 and then I am coming back to the P1. This is what the first case. Verify. So first I am executing P1. So C is equals to B minus 1. What is the B value? 2. 2 minus 1 in the sense 1. So now C is equals to 1. So after the first instruction of P1, I am taking the preemption towards the P2. See, I am telling you, preemptions you can take at any moment. Don't need of by hearting. You can. That's what the practice. Preemptions can be happened at any moment. Okay, preemptions can be happened at any moment. Preemption in the sense, one of the reason for the preemption is you can consider interrupt. At any moment, the interrupt may occur. Okay, so that's what we are saying here. So C, after the first instruction of the P1 is being executed, then suddenly we have taken the preemption. Then now we are finishing the P2. So if I finishing the P2 here, look at, so P2, D is equals to 2 into B. What is the B value? B value, is it changed here? No. So that the initial value of B is equals to 2 only used by this P2, which is D is equals to 4. Then this is executing B value as 3 now. After that, we are taking the preemption towards the P1. So P2 have finished and it has saved value 3 into the B. Now, I came back to the P1. So then B is equals to 2 into C. But what is the C value? 1. So now the B is going to rewrite this 3 value. So it means that B is equals to 2 at the end. With this execution, first I am executing the P1. Then I am taking the preemption with the P2, finishing up the P2, and then again coming back to the P1. With this kind of execution order, with the preemptions case, I am getting B value at the end as 2. So this is what case 1 in the preemptions. But when I consider case 2, if you consider case 2, so first I am executing P2, then I am coming to P1, and then again I will come back to the P2. Then what will happen? Have a look. So first I am starting with the P2. So P2, B is equals to 2. So then D value is equals to 4. Right. So after the execution of this first instruction of P2, I am taking the preemption towards the P1. Then C is equals to B minus 1. What is the B value? As the B value is not yet modified here, this for P1 also B value is 2. So that C is equals to 1. Then we are finishing this P1 completely. So B is equals to 2. So after finishing of P1 into the B, we have 2. So then we are taking the preemption towards the P2. Then B is equals to D minus 1. What is the D value? 4. So that B is equals to D minus 1 means 4 minus 1, B value is going to be 3. So now the P2 is rewriting this B value is equals to 2 as B is equals to 3. So with this kind of execution order, at the end, the B value is going to hold value 3. So overall, if you verify in these orders, what are the different values that B is holding here? If you verify, B is holding 1 time 3, B is holding 1 time 4, B is holding 1 time 2. So these are the three different values that are being saving into the B. So that 3 different values. So 3 is the answer for this question. So the number of distinct values that B can possibly take after the execution is 3. See, these type of questions you need to do more and more practice, because inter-process synchronization, every year you have one question as part of IIT Kanpur previous year papers. So when you have done so many questions based on this particular inter-process synchronization, then only you people can easily answer these type of questions. So I hope you are clear with this explanation. Let's move to next question. Right, so this is one question we have. See, so far we have covered one question from memory management, one question from inter-process synchronization. Now we are moving to one question from process scheduling algorithms. And this question is the most toughest question among all the previous year papers of operating systems, specifically process scheduling algorithms. Specifically, the topic I clearly mentioning, process scheduling algorithms. If you verify the questions of these process scheduling algorithms exclusively, among all of them, this is going to be. So how many number of questions we have from process scheduling algorithms? Among all those questions, this question is the toughest one. Okay, so very smart question. Verify how we can solve this. So consider a uniprocess system executing 3 tasks. So I am having T1, T2, T3, right? Each of which composed of infinite sequence of jobs. It means that infinite number of instances we can have with respect to this T1, T2, T3, which arrive periodically at intervals of 3, 7, 20 milliseconds. What does it mean? P1 can arrive, let's say, T1, T2, T3, all are, for example, at 0. Then this T1 again can come, again can enter into the ready queue at 3. Again it can come into the ready queue at 6. Every 3 intervals, for every 3 intervals, P1 can enter into ready queue. For every 7 intervals, P2 can enter into ready queue. For every 20 intervals or else 20 millisecond, T1 can T3 can enter into ready queue. That is what the meaning. So we'll see that. Okay. So the priority of each task is inverse of its period, and the available tasks are scheduled in order of priority, with the highest priority task scheduled first. Okay. Each instance, so for every instance or else for every appearance of T1, T2, T3, they are executing on the CPU for how much time? If it is T1, 1 unit of execution. If it is T2, 2 units. If it is T3, 4 units of execution. Okay. So given that all tasks initially arrive at the beginning of the first millisecond. So it means T1, T2, T3 all are arrived at 0 millisecond only. First millisecond, in the sense people may get confused with 1. That is mistake. First millisecond, in the sense 0 only, 0 to 1. That period also CPU should not be idle. So at 0 itself the CPU should be busy, right? It's not like 0 to 1. So people generally, while people are solving this question, you people may consider that all the processor arrived at 1. No, it is 0. 0 is the first millisecond. Then the first instance of T3 completes its execution at the end of milliseconds is. Let's see how we can solve. According to this question, it is mentioned that first let us calculate the priorities of T1, T2, T3. So the priority of T1 is what? Inverse of its period. Inverse of its period in the sense 1 by 3. The priority of T2 is inverse of its period, that is 1 by 7. The priority of T3, which is 1 by 20. So here T1 is having high priority. So this is high priority and this is low priority. Right? So then this T1 and T2 and T3, these 3 tasks can appear again and again in the ready queue for every 3 milliseconds, 7 milliseconds and 20 milliseconds. That's what we are going to say. Initially all are at 0. Again this T1 can enter at 3. Again this T1 can enter into ready queue at 6. Again this T1 can enter into the ready queue at 9. For every 3 milliseconds T1 can enter 12, 15, okay, and then 18 and then 21. So this way infinite number of times it can appear in the ready queue. Next, T2. So first time it is appearing at 0 in the ready queue, but after that the second instance is going to be appeared at 7 milliseconds. So 7. For every 7 milliseconds T2 is appearing into the ready queue. Means after 7 again it can appear at 14, 21. So this way it is also continuing till infinity. Then T3, first appearance in the ready queue is 0 and the second appearance is at 20 milliseconds. So for every 20 milliseconds it can appear. It means that after 20 again it can come to 40. Again it can come to 60. So this way infinite. This is the first basic to solve this particular question. So now we can have the Gantt chart for this question. So how we can draw the Gantt chart? Have a look. So at 0, T1 is there, T2 is there and T3 also there. So, but among these 3, which one is having high priority? T1. So the T1 will start execution. How long it is going to get executed? Only one time, because its execution time is for every instance of T1 on the CPU, it can execute only 1 unit of time. So that's why it is 1. Then by 1 in the ready queue, you have T2 and T3. Then among these 2, as the T2 is having high priority, T2 will be handed over to the CPU. And this T2 will be continued as for every instance of T2 will execute 2 milliseconds. Now it is appeared so that 1 to 2 means 1 to 3, 1 to 3 until this T1 gets executed, T2 gets executed. Then we are having in the ready queue only T3. But unfortunately, if you verify, this T1 is again appearing at 3. So at 3 again T1 is appearing now. Then among the T3 and T1, which is having high priority in the sense T1. So again T1 will start its execution. It is going to be executed till 4. Then if by 4 we are having only T3. So T1 is not coming back into the ready queue at 4 because T1 again can come back into the ready queue at 6. T2 can come back at ready queue at 7. Okay. But so at 4, as among the T1, T2, no one is part of the ready queue. Only T3 is the part of ready queue. So the T3 will start its execution. So this is going to be executed till 6. But you know, it is clearly mentioned that Preemptions are allowed, something it is given, yes, the task preemptions are allowed. So while this T3 is executing from 4 to 6, now T3 is in execution here, T3 is in execution, T1 is arrived, at 6 again T1 is arriving, so T1 is arrived. Then while this T3 is in running state, T1 which is having high priority is arrived, then what will happen? Preemption will take place. It means that T1 will start its execution. So T3 first instance is not yet finished. So what is the total? 4. Out of 4, only 2 units is finished here. Still it is having 2 units of remaining, right? So then T1 will execute till 7. Now, by this moment, T3 is there in the ready queue, and by 7, T2 is arrived. So among these two, T2 is having high priority. So the T2 will start its execution. It is going to be executed till 9. By 9, T3 is there in the ready queue, and by 9, T1 is arriving again. So among this T3 and T1, T1 is having the high priority, so the T1 will hand over to the CPU. So this is going to be executed till 10. By 10, in the ready queue, we have only T3. So this T3, if we start its execution, now by 10, again T1 is not coming, because T1 can come back into the ready queue at 12, T2 can come back into the ready queue at 14. So by 10, no one is there. So it means that T3 will start its execution till 12. So with this, T3 first time it is finished. First time completely T3 is finished. By 12, T1 is arrived. So again T1 will start its execution till 13. So this way it goes. But the point is, the first instance of T3 completes its execution at the end of dash millisecond. That is at 12. At 12 T3 is finishing. So that's why 12 milliseconds is the answer for this question. This is very smart question which is given by IIT Kanpur during the 2015 paper. Okay, so no specific algorithm like SRTF is not given, round robin is not given, but logic matters. Whoever is been able to understand this question, those people can easily able to answer this. And whoever is having the brief knowledge about the process scheduling algorithms, those people can easily answer to this question. So 12 is the answer for this question. Okay, so I believe you are clear with the explanation. Let's move to next question. Right. So this is the question we have from file systems. Verify. So in the file systems, if you verify in our yesterday's class, in our previous session, if you verify, every year you have one question from disk scheduling algorithms. So let's see one question now. Okay. Right. So here, suppose the following disk request sequence for a disk with 100 tracks is given: 45, 20, 90, 10, 50, 60, 80, 70, and 25. Assume that the initial position of the read-write header is on track 50. The additional distance that will be traversed by the read-write head when the shortest seek time first algorithm is used compared to the scan algorithm. Assume that the scan algorithm moves towards the 100 when it starts execution is dash tracks. This is also a very smart question I'm telling you. See, people generally, when it is given 100 tracks, how you people can consider in a silly mistake, you people can consider 0 to 99. Yes or no? But 0 to 99, the thing is, if you verify this line, assume that the scan moves towards the 100. 0 to 99, you are considering the range of these 100 tracks. If you consider 0 to 99, where you are able to see 100? No, right? So it means compulsory you have to consider from 1 to 100. Very smart question, right? So let's look into this particular question. So now we are considering 1 to 100. The track numbers we are considering 1 to 100. Okay? Right. So now we are having 1, let's say 1 to 100. 1 to 100. So after 1, we are having 10. Okay? 10. After 10, we are having 20. 20. After 20, we are having 25. 25. After 25, we don't have 30. and then we are having 45. So 45. After 45 we have 50, and then we have 60, and then we have 70. After that we have 80, and then 90. Right. Right. So, and it is clearly mentioned that the initial position of the read rate head is at 50. So it means here the initial position of the read rate head. So for example, if we execute SSTF, shortest seek time first, what is the concept of SSTF? From the current head position, which disk request is nearer to that the read rate head can move. Correct? That is what, it is a kind of SJF concept. In the process scheduling algorithms, if we consider SJF, shortest job first. So from the current read rate head position, among the disk request, which one is very close to that request, the read rate head can move. This is what shortest seek time first. Let's see. So 50, what is the distance between 50 and 45? 15. But what is the distance between 50 and 60? 10. So it means that from 50, the disk read rate head goes to 60. So what is the travel distance here? 10. Then from 60, 45 is in the distance of 15. Right? 15. So if you verify here, okay, so let's consider this. A small mistake is being committed by me. So please verify. So from 50, if you verify from 50, 45 and 60 if you verify, which one is the shorter distance? 45 is the shorter distance because the distance is 5 here, but the distance is 6 here, 10 here. So 5 is the shorter distance. That's why from here to 45 it goes. So what is the travel distance? 5. From 45, is the 25 is in shorter distance or 60 is in shorter distance? From 45, 25 is in the distance of 20. But from 45, 60 is in the distance of 15. So this is the shorter distance from 45. That's why it goes to 60 now. So what is the travel distance? 15. Then from 60, is the 70 is in shorter distance or 25 is in shorter distance in the sense? 70. So from 25 to 60, we are having 35 is the distance. But here from 60 to the 70, it is 10 only. So that's why we will go to 70. This is 10. Then from 70, is 80 is in shorter distance or 25 is in shorter distance in the sense? 80 is in shorter distance. So that's why we will go to 80 here. That is the travel distance of again 10. Then from 80, is the 25 is in shorter distance or else 90 is in shorter distance? In the sense 90 only in shorter distance because 10 here, but there it is around 55. So it is in shorter distance. So it is again 10. So in this way, it is been covered. I mean, it has serviced all these disk requests. From 90 it comes to 25 now. Now it comes to 25. So from 90, is the 25 is in shorter distance or else 20 is in shorter distance in the sense 25 is in shorter distance. So that's why from 90 it comes to 25. So what is the travel distance? 90 and 25. If we consider 65 is the travel distance. So from 25, is the 10 is in shorter distance or else 20 is in shorter distance in the sense 20. So we will go to 20. And the travel distance is 5. So from 20, we will go to 10. So what is the travel distance? 10. So now verify what is the total distance that has been traveled by this disk read rate head to service all these disk requests is 15 plus 5, 5 plus 15, 20, 20 plus 10, 20 plus 10, 30, 40, 50. 50 and then let's say it is 60. Okay. Then 60 plus 70 if you verify. So 5 plus 65 which is 70. Okay. So this is 70 and this is 80. 80 and 90, 100, 110 and 130. So with the SSTF, the travel distance we are having is 130 with SSTF. Then we are going to see with the scan, So now we are going to see with the scan. Right. So now if we consider with the scan, so what is the travel distance we have? What is the disk request? 110, 20, okay, then 25, then 45, and then 50, and then 60, 70, 80, 90, and 100. So this is one end of the disk and this is another end of the disk. And it is clearly mentioned in the scan algorithm, in the scan, the discrete head is moving towards the 100. It means from 50, as the initial position is at 50, from 50 it goes towards the 100, means from 50 it goes to 60, then 70, and then 80, and then 90, and this is what the difference here. Scan touches in which direction it is traveling, in that direction the end point also can be touched by the scan. So it means after servicing this last discrete request in this direction, it goes to even ending point also. And then it takes the reverse. So while it is in reverse, whatever the disk request is appearing, that disk request also gets serviced. But in the C scan, it won't service the disk request, while after taking the reverse, it won't service in between disk request. Directly it comes to the end point and then it takes the reverse direction. But in the scan, when it takes the reverse direction, in that reverse direction, if there is any disk request is arriving, that is also serviced by the disk read head when we are applying scan algorithm. So now this is a 10, it is 10, it is 10, and it is 10, and it is also 10. Now 100 to 45, 100 to 45, how much it is? 55. And 45 to 25, how much it is? 20. Then 25 to 20, how much it is? 5. Then 20 to 10, how much it is? 10. And it won't touch the next end point. Only one side, in which direction it is traveling initially, in that direction only the end point can be touched by the discrete head when we apply scan scheduling algorithm. Okay, right. So now this is 1, 2, 3, 4, 5, 50, 50, then it is 60, 60 plus 20, 80, right? 80 plus 60 if you verify, 140. So with the scan, we are having 140. With the SSTF, we are having 130. So it is saying that, what is the question it is saying? The additional distance that will be traveled by discrete head when the shortest seek time scheduling algorithm is used, compared to the scan algorithm is, what is the additional distance? Here you are having 140, here you are having 130. It means 10 tracks is the additional distance. So 10 is the answer for this question. Okay, so this is the way how you can handle this disk scheduling algorithm based question. Right. Let's move to next question. Right. So this is another question we have from page replacement algorithms. So what is the question here? If you verify, the question if you consider, this is the page reference string we have, okay, and we are applying both LRU and FIFO. So let's consider first this LRU. If you consider first in first out, let's consider first in first out. If you consider, so first if we consider first in first out, so we required the page references here. What are the page references if we consider 382, so 382, 391, 391, 638, 638, then 936, 936, and then 213, 2, 1 and 3. So the question clearly mentioned that, how many page frames we are having? 5 page frames. It is clearly mentioned there are 5 page frames. Okay, so 5 page frames we are considering here. So the memory contains 5 page frames. So initially the CPU is willing to access page number 3, but page number 3 is not there in the main memory because initially all 5 page frames are empty, right? So Since CP is willing to access page 3, as the page 3 is not part of the main memory initially, you can say that it is resulting a page fault, and we are bringing that page 3 into the main memory like this. Now, CP is willing to access page 8, but page 8 is also not part of the main memory by the time of its reference. Then, as page 8 is not part of the main memory, you can say it is page fault, and we are bringing that page 8 into the main memory. Now, CP is willing to access page 2. By this moment, by the time of reference of page 2, we are having only 3 and 8 in our memory. So, it is also resulting a page fault, and we are bringing that 2 from secondary memory to main memory. Right? So, now CP is willing to access page 3, but page 3 is already there in the main memory, right? So, this is going to be a hit, page hit. So, 382, right? So, then the CP is willing to access page 9, but page 9 is not part of currently main memory. So, page 9 is resulting a page fault. So, 382 and 9 we are bringing into the main memory. Now, CP is willing to access page 1, but page 1 is not part of currently main memory, which is also resulting page fault. So, that 3, 8, 2, 9 and 1. So, now the memory is full. Now, CP is willing to access page 6. So, page 6 we want to access. But page 6 is not part of currently main memory. Then which page we need to select for the replacement? If it is FIFO algorithm, so for example, if I am applying FIFO algorithm here, among the 38291, which page is entered first? Verify. 3 is entered here, 8 is entered here, 2 is entered here, 9 is entered here, and 1 is entered. So 3 is entered first. So that 3 is going to be the victim now to get replaced by this 6. So now 6 is going to replace this 3, then 6, 8, 2, 9, and 1. So this is also a page fault. So now the CP is willing to access page 3, but page 3 is not there in the main memory, which is resulting page fault. Then among the 68291, which page needs to be selected as a victim? So if you verify 6 is just entered, but 8 is entered here, 2 is entered here, 9 is entered here, and 1 is entered here. So 8 is the first page among these pages which is entered first in the main memory. So that 8 can be the victim here. So 6, 3, 2, 9 and 1. So now the CP is willing to access page 8. But page 8 is not part of current main memory, which is also resulting a page fault. Then, among the 63291, which page needs to be selected as a victim to get replaced? If you verify 6 is entered here, 3 is entered here, but 2 is entered here, 9 is entered, and 1 is entered. So 2 is entered first. So the 2 is going to be the victim here. So 6, 3, and 2 gets replaced by 8, 9, and 1. Now CP is willing to access page 9. Page 9 is already there in the main memory. So that it is a hit. So 6, 3, 8, 9, 1. So now CP is willing to access page 3. Yes, page 3 is already there in the main memory, which is resulting again page hit. So 6, 3, 8, 9 and 1. So now CP is willing to access page 6. Page 6 is also there in the main memory, which is resulting a page hit. So that 6, 3, 8, 9 and 1. Now the CP is willing to access page 2, but page 2 is not part of currently main memory. So among the 6, 3, 8, 9, 1, which page is entered first? If you verify, 6 is entered here, 3 is entered here, 6 is entered here, 3 is entered here, right? 8 is entered here. And 9, if you verify, 9 is entered here and 1 is entered. So 9 is going to be the victim here. So 1, 2, 8, 3 and 6. This is going to be the page fault. Then 1. With respect to the 1, it is already there in the main memory, which is resulting a page hit. So 3 is already there in the main memory, which is resulting a page hit. So 1, 2, 8, 3 and 6. So total number of page faults with FIFO, if you verify, 1, 2, 3, 4, 5, 6, 7, 8, okay, 9. So we are having 9 number of page faults we have. So 1, 2, 3, 4, 5, 6, 7, 8 and 9 number of page faults we have, right? So now let's consider LRU. So LRU, I am considering LRU now, verify. So 3, 8, 2, 3, 9, 1, 6, 3, 8, 9, 3, 6, 2, 1 and 3. So it is a page fault 3 and it is also resulting page fault 8, 2 also resulting a page fault 3, 8 and 2, it is also resulting a page fault. Now 3, this is resulting a hit which is already part of 3 is already part of the main memory. Now 9, it is not there in the main memory which is resulting a page fault. So 3, 8, 2 and 9. Now 1 is already also not there in the main memory which is resulting a page fault. So then 3, 8, 2, 9 and 1. So now the memory is full. Now 6. So verify among these 3, 8, 2, 9, 1, 1 is the most recently used. After 1, 9 is the next most recently used. After 1 and 9, 3 is the next most recently used. Then 1, 3, 9, 1, 9, 3, after these 2 is the next most recently used, but 8 is the least recently used. So 8 is going to be the victim here. But in the case of FIFO, 3 is the victim, but LRU, 8 is the victim here, right? 8 is the victim. So that's what we are going to do. So 3 and then 6 and then 2, 9 and then 1. So this is a page fault. Now 3 is already there in the main memory. So 3, 6, 2, 9 and 1, page hit. Next 8. 8 is not there in the main memory. So verify now. 3 is the most recently used. After 3, 6 is the next most recently used. After 3 and 6, 1 is the next most recently used. Comparatively 3, 6, 1, next most recently used is 9, but 2 is the least recently used. So 2 is going to be the victim here. So now 2 is going to be the victim, right? So 9, 1, 6 and 3. This is a page fault. Now 9 is already there in the main memory, right? So 1, 9, 8, 6 and 3, it is a page hit. Now CP is willing to access page 3, but page 3 is already there in the main memory, 3, 6, 8, 9 and 1. So this is a page hit. Now 6 we want to access, 6 is already there in the main memory, which is also resulting a page hit. Now 2 we want to access, but 2 is not there in the main memory. Then verify, 6 is the most recently used, after that 3 is the next most recently used, after that 9 is the next most recently used. So 6, 3, 9 I cannot replace, 8 also, but 1 I can replace. So that 1 can be replaced by 2 now. So 2, 9, 8, 6 and 3, which is a page fault. Then 1 I have to get, but 1 is not there in the main memory. Then 2 is the next most recently used. After 2 is the most recently used. After that 6 is the next most recently used. Then again 3 is the next most recently used, right? And then 9 and then 8. So 9, 3, 6, 2 is here. 8 is the least recently used. So that 8 can be the victim here. So 1, 2, 9, 1, 6 and 3, which is page fault. And this is going to be page hit. So 2, 9, 1, 6 and 3, which is going to be page hit. So verify now how many page faults we have. 1, 2, 3, 4, 5, 6, 7, 8 and 9. So if you verify, LRU is resulting 9 page faults and FIFO also resultant 9 page faults. So FIFO also have result 9 page faults. So both are resulting the same number of page faults, so that option A, which is both incur the same number of page faults, is the answer for this question. So this is the way how you can do the questions based on this page replacement algorithm. See, in this session I just recalled you one question on page replacement algorithm, one question we have done with the disk scheduling algorithm, one question we have done with the process scheduling algorithms, one question we have done with the synchronization, one question we have done with the memory management. All the important concepts we have revised with questions, right? So this is the way how we can handle several questions. There are several questions. That's what I strongly suggest you all, that before appearing to the GATE examination, I strongly suggest you that you people please go through the GQB questions, the previous year GATE questions 2 to 3 times at least. So that different types of questions you can encounter, and again, whenever you are able to solve them, then your confidence can be grown up. Okay, so I hope the session is helpful to all of you. All the best for your examination. Thank you.